Okay, so why don't we get started? Questions? Okay, guys, ready? Bring it up front, okay? So questions anyone has on any of the homework, any problems, stuff like that? Okay, so I think I mentioned in the announcements that I'm going to try to tweak the homeworks a little bit. So if there's a numerical response, I'll give you guys 3 attempts just because you can enter things wrong. Most multiple choice, I'll tend to do 2 attempts because usually you have 4 choices. You should be able to kind of intelligently rule out one of them, right? That's kind of the idea. Okay, so what I want to do is I want to kind of pick up where we were talking about last time. We were talking about plotting quantitative variables. So we said, okay, we have this question. What do? We collect data, and then we're going to summarize it, right? So we said the way that we always summarize data, this is kind of our big picture, right? Question, collect data. Then I want to try to summarize the data. And we said the way we always do this is the same process, right? I'm going to make a table of the values. I'm going to make a plot, and then I'm going to describe this plot. And for categorical variables, there wasn't a lot we could do, but quantitative is a lot more complex, okay? So we want to talk about a new type of plot today called a box plot. So the last time we said when we have really small data sets, we make dot plots, right? Just plot the values on a number line. We talked about histograms yesterday, or last class, which is kind of a more detailed picture for these larger data sets. But the problem with histograms sometimes is that their appearance can depend upon how you bin the data values. If you make the bin widths a little bit different, the appearance can be also different looking. And we don't like that. That's sometimes not a good thing. It doesn't happen a lot, but sometimes it happens. The other problem is that it gives a very detailed picture of the data. And you might think that's a good thing. The more detail, the better, but not always. For example, when we're comparing 2 different distributions, like maybe we have people before and after some sort of treatment or some sort of before ad campaign, and we want to look and say how much they spend before and after the ad campaign, sometimes having a lot of detail is actually distracting. So sometimes we just want to make a kind of grosser, lower level plot, okay? The other problem with histograms that we're going to see is that identifying outliers can be difficult. That's going to actually be a really important thing for us to be able to do. So we're going to introduce this thing called a box plot. It's kind of a low resolution picture of the data. And what's really nice is it starts off with a very simple table. There's no bins or anything like that. We're going to basically create this table of these 5 numbers called the 5-number summary. And we're going to talk about what Q1, Q2, and Q3 are in a minute. Let me kind of show you an idea of what a box plot is. Try to draw this. So here's the basic picture. I have some quantitative variable. So this is just going to be a number line. So these are going to be the values of my quantitative variable. Okay? That. And the idea is that I'm going to start off kind of like a dot plot, just for the sake of kind of illustrating what's going on, okay? So maybe my data points kind of look like this. And what I'm going to do is I'm going to bin by quartile, which is what I'm thinking about later. So I'm going to start with the 25th percentile here. So this data value here is called Q1. It stands for the first quartile. And this is essentially the 25th percentile. So what does it mean for a data value to be the 25th percentile? What does that mean? Yeah, in a sense, if I'm going to build it right, it might not be actually the 25th value, but what we're saying is 25% of the data set is going to lie below this value, right? So 25% of my data values are going to lie below this. Okay? And so Q stands for quarter, right? 25, first quartile stands for like 24%. If you had an SAT score that was in the 25th percentile, would that be good or bad? Bad. Because it means 75% of the people scored above you, right? You actually be really above, right? And so we're going to look at the third quartile, which we call Q3. So you think of it kind of like quarters, right? 1 quarter is 25, 3 quarters is going to be 75. So this is a 75th percentile. In other words, 25% of the data values lie above it. And we have in the middle the second quartile, and that's the 50th percentile. That goes by another name. That's called the median. So Q2, which is a second quartile, also goes by the name the median, and this is the 50th percentile. Okay? And so the median of a data set is just like the median of a highway. What is the median of a highway? It's just the highway in the park. That's what the median is. 50% of the data is below the median, 50% above. Okay? And what we're going to do is we're going to make a plot of this. So here's how the plot's going to look. And we're going to make a box. So this is sometimes called a box and whisker plot. So the lower end of the box is going to be where the first quartile is, which is around 6 in this case. The third quartile is going to be the upper end of the box, which is around 10. And the median is just going to be a line drawn wherever it is. So in this case, the median is around 8. And then the whisker is going to be the rest of the data set. It's going to generally extend out to the lowest and the largest value. Okay? So it's a very kind of gross way of representing the data. Very different than a histogram. Okay? Now, there's a little bit more we need to do with the box plot. So here's the idea. Let's go back and look at the F16 data that we have. So I asked you guys to load up the F16 data set. And the first thing I'm going to do is I'm going to make this table. Okay. So for the F16 data, I'm going to make this what we call 5-number summary. So here I'm going to have the maximum value in the data set, the value of the third quartile, the second quartile, the first quartile, and the minimum. And you could do it by hand, but I'm going to use StatCrunch. It's a lot easier, okay? So I'm going to get these values. So let's go back to StatCrunch. And I'm going to click on Stat, Summary Stats, Columns. And I want to look at the variable accidents. And I'm going to pick out these values now. So what do I want? I want the minimum value. I'm going to hold Control. And now pick out the maximum value. Q1, Q3, and I want Q2, which is actually the median, right? And I'm going to go ahead and hit Compute, and it'll give me those values. Okay. So let's just make sure that everyone's on the same page. Everyone's getting this. Okay. So stats, summary stats column, right? We're going to start off here. So stats, summary stats column. And then you're just going to click each of those attributes. Let's see, so we want to choose the mean. I'm sorry, we want to choose the median, Q1, Q2, max, and min, right? That's the 5-number summary. So we want to choose the following 5 statistics. Maximum value, Q3, Q2 is called the median, right? Q1, and then the minimum. We want to choose those 5 values. Okay. I'm sorry? Which one? Oh yeah, let's see. What did I do? Let me just. Yeah, we don't need it. If you do more, it won't hurt. I think this kind of just did it on its own, to tell you the truth. I had them selected. Oh, okay. Actually, what happens is the default is it highlights them all. So I didn't choose anything. Yeah. So I just want to kind of show you guys what to do. Yep. Now all you do is Q1 and Q3. Five numbers, right? 5 statistics we need to get. Is it not working? Okay, so stats, summary stats, columns. Okay. Are we guys good? Okay, and now just go ahead and hit compute, and you're good. Excellent. Looking good. Okay, go ahead and do compute. Excellent. How's it going? Okay. Got it? So you can hold down like the control key and you can shoot it. Actually, you don't want to do N at all. So this is just a default. Okay. So I didn't really need for you guys to do what's on here because I've already done it. So you hit Q1, Q3, right? Min, max, median. Those are the 5 guys we want. Okay. All right. And so these are my numbers. When you look at what you get from the program, you get 0 for the minimum. Q1 is 5, Q2 is 9, Q3 is 14, and the max is 23. That's my 5-number summary. Now I'm going to plot that, but it's not going to be quite as simple as that diagram that I showed you. So here's kind of the idea, okay? Here's what I'm going to do. I'm going to plot a number line, and I'd like you to do this by hand. So go ahead and get out a piece of paper, because on the homework you'll have to do it. And even on the quizzes and on the exams, I might ask you to do it by hand, right? The quizzes and exams won't all just be multiple choice. I could ask you to take a picture and to post it, right? Something like that. So again, these are going to be our values. So this is the number of accidents down here. Okay. And it goes from 0 to about 23, so we'll just do something like this. Whoops. Okay. Notice that there's no y-axis. Okay. I'm just showing the location of kind of markers in the data set, right? So first I'm gonna put down Q1. Q1 was 5. Okay, so this is Q1, it's the bottom of the box. And we said Q3 was 14, so the box is gonna go up, kind of use your calibrated eyeball, right? It's gonna go up to about here. So this is Q1, this is Q3. And then I'm gonna put the median in. The median's just gonna be a straight line, and that's at around 9, okay? So that's the box plot. Now here's kind of the idea behind what we're doing. We want to kind of look at all of the data that belongs to the same type of group. Okay? So I think of this as like a house. And now we're going to define like a boundary. And everything in that boundary is going to be considered part of the population we're interested in. So here's what we're going to do. We're going to compute this thing called a fence length. And basically, this is going to be the length outside of the box where data points can go before they become considered outliers, okay? So I can go as far out as the fence length past the box, and then I'm an outlier. So how do we get the fence length? Well, what we do is we compute the length of this box. Okay. The length of this box is called the interquartile range, IQR. And it's equal to the value of the third quartile minus the first quartile. So people call this the interquartile range. And really it's just the length of the box, right? Think of it as the size of the house, okay? And so in this case, what do we have for the IQR? Well, the IQR is just Q3 is 4, Q1 is 5, so the length of that box is 9, right? And the way we're going to define this fence length is going to be 1.5 times the length of the box. So this fence length is going to be equal to 1.5 times the interquartile range, which in our case is 1.5 times 9, which is going to be 13.5. So I can go 13.5 on both sides of the box before I'm considering an outlier. So let's go ahead and figure out what those values are, okay? I'm going to put a little dotted line. I'm not going to plot this, but I'm going to put it down here. This value goes out to, this value is Q3 plus the fence length, which is, Q3 was 14 plus 13.5 is 27.5. So sometimes people call this the upper fence value. This is as far out as I can go. That's 1.5 times the IQR half into that. Now, here's what we want to figure out. What is the data value that's as close to 27.5 but still within that fence? What is it? Sorry, what is it? 23. 23 is the largest value that's still within that fence, and that's what I'm going to plot. That's the whisker part. So this value right here, 23, this is the largest value within the fence. Okay? And this is the whisker. The upper whisker. Yeah. Okay. Right, so what I'm going to do is I'm going to go one fence length outside the box, okay? So my box is at 14, and my fence length is 13.5. So I'm going to go 14 plus 13.5. Right, so 1.5 fence length past Q3 is 14 is going to be 27.5.
What's that?
So some people publish, the book calls this the upper fence value. You know, I hate giving need for a copy of it, but that's what it's called, the upper fence value. And why is it 1.5 times the fence length? We're gonna come 1.5 times the IQR. We're gonna come back to that later. Okay, so let's look on the other side. So here I'm at 5, right? So if I go one fence length below, this value ends up being Q1 minus the fence length, which is 5 minus 13.5, which is minus 8.5. So this is the lower fence value. Okay? Can't read my handwriting, let me know. It's hard to write, and my handwriting's not the best. Okay, Q1 minus the fence length. Okay? Okay. So what is the smallest? Yeah, go ahead. Right.
So when you develop past 0, you have to draw the plot.
Yeah, so that's our next question. What's the smallest value within that fence line? And of course, we can't go below 0 and have a value. that's what I'm going to plot, okay? So the smallest value within that lower fence is 0. That's right. And there's my plot. There's the box plot. If I had a value of 29, I would indicate that as an outlier. And the way you'd show that is you would put a little star. So there'll be like a little special symbol when the program does this, okay? So if you have an outlier, if I had a value past this fence length, it would show up as a special symbol, usually like a circle or a little star, okay? That indicates that it's outside the fence. It's an outside, an outlier, okay? So any questions about this guy?
So do you put the, you know, you have the lines at the end of your list, would those be on your lower and upper fence length, or where your minimum? Click on.
Okay, so yeah, so that's the old thing. So you need this value right here, this little line here. Okay, we never actually plot that. Right. We have to compute it, but we never actually plot it. So when we're done, we come back very cleverly and we erase this. Okay. And all we plot are the maximum mean values within that fence. We don't actually plot. So I just do it just to kind of illustrate the first time what's going on. But when you do it, now that you know what's going on, you won't even bother plotting it. You'll just compute it, and you'll find the furthest value within all of that. Just for illustration purposes only. Yeah. Oh, you mean what would happen if the maximum value landed right on the fence? Oh, I would actually still leave it. So suppose you had a value of 29 and then you still had 23. The whistle would only go out to the longest value within the fence. And then anything outside the fence, I would say I'll click and rotate. Okay? So it takes a little while to kind of get the hang of this. But that's what's going on. Okay, shall we try to do a stat crunch so we can do it the easy way? All right. So let's go over to stat crunch now. And we'll just go to plot, box plot, graph, box plot, click on accidents. And this is one of the few cases where these little boxes that normally we just kind of say, if you click or not click, are actually going to be important. This box right here you have to check. So this is going to now denote outliers as individual points outside the fence line. If you don't do that, what it does is it just draws the whiskers out to the maximum values. And we don't want that. And why that's even an option, quite honestly, I don't know. Because it really shouldn't be. Now you have your choice. The default is that it plots the box plot vertically. That is useful if you're comparing two different distributions. That's really nice to have them side by side and vertical. Usually when you plot just one, it's usually easier to do it horizontal. But that's your discretion, okay? I'm going to go ahead and put the axes labels in here. So this is accident rate. There is no Y label, so you can make this as wide or as fat as you want. I mean, you want to make it so it's kind of pleasing to the eye, but there is no Y label. This is not like a histogram. And then you go ahead and put your title. So I'd say box plot of F16 Class A accidents. Okay, and you hit compute. And the default color is kind of ugly. It's like a blue, and it's actually really hard to see that line. So if you want to make it a little nicer, you can edit it and change the color from 7 colors to like something soft. And then it looks a little bit nicer. Looks good. All right. Good deal. Okay, everybody's looking good. Is it still moving up or what's going on? Okay. All right, great. Now, here's the thing to kind of bear in mind is that the box plot and the histogram, it's kind of useful to look at them together. So let's just kind of see what information they give us. So I'm going to kind of squash this down a little bit like this, and then plot the histogram. And I'll say values above bar and do the relative frequency. Okay? So this is just like the plot we did before. And I'm going to try to stretch them out so that they're on the same, they have the same sort of x-axis lengths. Okay? So they're both kind of starting at 0. And that's like 20. And it takes a lot of manipulating. You don't have a little bit of it. Okay. But here's what I want to point out. I want to point out that these things are actually complementary. So notice that 5 is pretty close to the first quartile. What you're seeing is 19% have 4 or less, right? So it kind of makes sense that this is the first quartile. There's roughly 25% below 5. Notice that the median was 9, and you can see there's 51% that have 9 or less, okay? This is kind of fitting together. This is from the 50th to the 75th percentile, so 25% of the data lies in here. And finally, the last 25% of the data lie up here. These two things are kind of complementary, all right? Okay, questions that we have about the box plot? Everybody's pretty good? All right, good. One of the things about the box plot that's bad, and you want to think about this, well, actually, I'll come back to that point in a second. We'll talk about that a little bit later. So just to kind of summarize about plots, okay, when we have small sample sizes, like 10, 20, we usually try dot plots, okay? When the sample size is large, we're going to use box plot or histogram. Generally, we do both, just to be on the safe side. And with box plots and histograms, they give different types of pictures. Histogram is more detailed. Box plot is kind of lower level, all right? So I'll tell you what, why don't we take a real quick break? We'll come back and we'll talk about how to describe the plots after this, okay? you guys. So let's start there. So were you referring to the fact that you're making the role, or that was that?
Well, I did it actually.
Yeah, okay, all right. Yeah,
But
so I haven't printed out the new role.
so you know, it's on campus. Like I can pull it up right now on my phone. But when I get on my computer, little quick.
How long does it let you stay in?
Maybe 3 minutes, and it'll literally just end the whole page. Say arrow 4, 0, 1.
Okay, so the thing to do is, and I know how to solve this, if you call the help desk, which is 226, I think it's 691, I can check it. There's the IT help desk, and
What's the number again?
I believe it's 266 69 I believe.
26.
Or 226 6910, I believe. I have it actually on speed dial in my office. I call them so often.
Okay.
If you call that, and you can actually check out the class.
Is it what's the area code?
Well, it's 386, so it's good every row. And if you call the option 3, lets you go right to Canvas. And that's the Canvas support option. They're really good. And I can check if it's that's not right because I have the number on speed dial. I call them a lot actually. And they're really good. But that sounds like something with either it's a browser or settings issue.
I think maybe because I was added to the class late after Anna dropped.
It shouldn't affect timing out though. There's something else I think going on because I mean once you're in, you're in. Yeah. It shouldn't be any problems after that. So something else is going on. Do you have other classes or other classes?
Because I have only one more class other than this class, so that's it. And I go out there.
If that number doesn't work, let me know. Because like I said, I have it on speed dial, and then we can work it out. All right. So why don't we say we snap back into it, okay? So here's what we want to do now. We want to talk about how to describe these plots. And so for a histogram, so we kind of talked before about you have a picture of somebody, right? What do? If you want to describe them, you pick out the main features. So we want to pick out the main features on a plot. And again, it's not just a matter of checking off boxes. It's really knowing why we're doing this, what we're actually looking for, okay? So I'm going to make a little table here. I'm going to make this on the board, okay? It's just easier. So we're going to what we're looking for and why, okay? And so the 5 things that we're going to look for is we're going to look for the number of modes. So when we did categorical variables, we said mode was the category that occurred the most, right? Well, with quantitative, you can have more than one mode. And really what we're looking for here is the local peaks, all right? We're also going to be looking at the shape. So we want to know, is it symmetric or not, all right? Symmetric or skewed. We want to kind of ask, where is the center of the data set? Where are the values clustered around? We want to know how wide the data set is. And finally, we want to know if there's any outliers. And so we're going to actually spend a lot of time. We're going to spend about 2.5 class periods just kind of going through how we describe histograms. Because it's a kind of involved process.
It goes by the axis.
I'm sorry?
It goes by the axis line.
I'm not quite sure I follow. Go ahead.
The width of the data set.
So the width of the data set, kind of, we can measure a lot of different ways. We can talk about standard deviation. We can talk about the interquartile range, okay? Or we can talk about the range and which one's appropriate. We're gonna kind of discuss. And it turns out that these things are all kind of interrelated too. So first of all, we can talk about the number of modes. And what we're talking about are the number of local peaks. And so there's really only 4 different ways that we describe this. The first is what we call uniform. In other words, there is no mode. They all occur with roughly the same frequency. So if you think about, for example, rolling a die, right? If we think about, the numbers 1 through 6, they're all going to occur with roughly the same frequency, okay? If we have one local peak, we call this unimodal, one mode, like unicycle, right? One wheel, okay? 2 modes, bimodal, like bicycle, right? 2 modes. And if we have more than 2, we don't try to put a fine point. We don't have trimodal and tetramodal. We just say it's multimodal. And that occurs really rarely. What do you think about this one right here? Do you think it's unimodal or bimodal? Could that be bimodal?
It could be, it seems like.
It could be, right? How do we? Oh, go ahead. Go ahead. No, go ahead.
No, I don't want to. Go ahead.
No, please go ahead.
No. Go.
Because here's the thing.
I don't want to like just jump ahead like.
No, go ahead, jump in. That's what this class is for. That's what makes it interesting. Hey, listen. Me standing up here talking about stuff I learned 20 years ago doesn't really throw me. I like hearing your ideas. So go ahead.
Well, because we have the occasion of both of them actually on an equal level, so that makes it unique from the bimode. The bimode, as you can see, only has two, and it's separate away from each other. But over here we have multiple occasions where they're equal to the same height, so that way what makes it unimodal.
So yeah, to kind of paraphrase what you're saying, to put a little finer point on it, this is no doubt bimodal. Why? Because they're separated a great deal. The question is, what do you do when they're not so well separated? And then it isn't so obvious. So there's kind of two ways of looking at this, okay? The one way is you could say, well, I think it's unimodal because what am I trying to do? I'm trying to draw a smooth curve. So I can see a smooth curve kind of fitting through one hump. And I can think of that little blip here as just being a little variation, right? But sometimes that doesn't happen. So here's what happens sometimes. If you think about, say, heights of men and women, and you plotted a histogram, okay? It used to be that women and men had very different heights. Now women are getting a little closer to the guys. So if you plot the histogram for women, they look kind of like this. And the histogram for men would look kind of like this. But if you looked at them together, they might look kind of like this. And then the question is, what do you do? Do you say to yourself, well, I think this is really, in my mind's eye, I draw this nice curve, and I think this is one nice distribution, or do you say that it's two different populations? And you might have to look. In this case, I might go back to the data and I might look and see, are there actually two different populations? Okay. So what we're looking here is we're looking for when we're looking at the number of modes, we're looking at the number of distinct peaks. And the question is why. So let me kind of give you an example of why you might be interested in this. So this is some data from 2008. I took all the professional golfers that year who competed and computed their average drive. Okay, how far they hit the ball off the tee, right? And so this is the histogram for the average drive of all the professional golfers. Definitely bimodal, right? Why do I have two peaks? Why do you think I have two peaks? Women and men? Right. I didn't say that they were men golfers. So this is the LPGA and the PGA. These are the women's drives. Okay. Roughly, there might be some women way out here, and this is mostly the men's drives. So why we're interested in how many modes? Because it's evidence of subpopulations. Okay. This is the idea. So why are we interested in this? Because we're looking for subpopulations. Knowing that there are men and women in that data set, I would definitely split them apart and look at them separately, right? In business, this happens a lot. There are a lot of subpopulations. Think about demographics, right? Male, female, young, old. There are a lot of situations like this, so you have to look at the number of nodes carefully. So now we want to look at shapes. And again, we don't put really a fine point on it. What we're interested in is this histogram symmetric? In other words, is there some kind of line I can draw through it so that basically it looks like a mirror image of itself, right? That would be symmetric. Or does it have a tail? And if it has a tail, we call a tail in statistics skewed. Yeah.
That last key was supposed to be on the complete rise and never had a depression into it. This looks like a little less symmetric.
So there is.
I'm just curious.
So the thing is, you're not trying to put a really fine point on it, right? So here's kind of the idea. When we have a tail, we call it skewed. And what we report is the side the tail is on. So this, I would say, if I'm drawing this best fit curve, right? I would say this looks like that. This looks like a tail, kind of like a dinosaur, right?
I know what I'm talking about is it looks exactly, well, not exactly similar to a symmetric, considering because a left skew or a right skew means that, like you said, the tail starts from the left or the right. But the curiosity is that it goes up, it keeps on going on the rise, not up in a depression. It has a depression, it's just a micro depression on the opposite side of the tail. But this looks like it completely drops back to another tail, so it makes it look symmetric.
So which one? 1, 2, or 3?
No, I'm talking about 1 with 2, not 3. 3 actually looks like it actually has a right skew because it goes from not really a noticeable left depression, but it actually goes. I'm sorry, from a right depression. It actually has somewhat minor left right depression, but it goes into a great right depression over there. So it looks like it is a right skew.
So here's kind of one way of thinking about it. Data sets are never perfectly symmetric, especially small data sets. You're never going to get them to be perfectly balanced. And in fact, if you see something that looks perfectly symmetric, the first thing I think personally is somebody fudged the data. That's the very first thing I think in my mind when I see something that looks perfectly symmetric. Very rare. So we're not trying to be really, really careful about this. We're saying, which does this look more like? Does it look more like it's symmetric or more like it has a tail? And it's a little bit of a judgment call. So sometimes when I'm not sure, like if I saw something in between this, and you see it a lot with real data, I might say it's approximately symmetric with maybe a slight left skew, if I'm not sure. But what we're going to see is that usually with financial data, it's really clear. There's not a lot of ambiguity very often, okay? So we're going to see that the shape is actually important because it tells us about these 3 other things. It tells us about outliers, and it tells us about how to compute the center and the spread. So we're going to see the shape is really important. So here what we're looking for with shape is we're looking for symmetric versus a tail.
And that's what I was trying to mention. Because, symmetric, it completely tells you that this is on the fine and then on the depression again. But if it's on a skew left or right, it means that this is going from a depression period into a rise period. And then if it's on the right, it went from a rise period to a depression period.
I see what you're saying.
Yeah. This one has the similarity of the symmetric, and that's why I'm like, okay, is it a symmetric or is it a left skew?
So you gotta be careful because this is talking about time series, and we're not looking at time. We're just basically binning the data. I'm looking at the values and I'm binning them. So here I'm saying that there were a few data values that were really small, okay, down in this tail. But we're not looking at a time series. I'm not looking at this like a time series, right? I'm kind of looking at the quantity. So let me kind of come back though. Hold that thought for a minute. So what I'm going to do just for a minute is I want to kind of go back to this histogram of box plot, and what I want to point out is that from a histogram you can see asymmetry, but you can see it from a box plot too. For example, this tail that's occurring, you're going to notice it in the asymmetry of the whiskers, right? That tail stretches out that lower whisker. And you also notice that the median's affected. The box part is stretched too. Okay? When you're right skewed, again, notice the asymmetry in the whiskers. And notice this portion of the box is getting stretched out. When it's symmetric, the whiskers will be about the same length, and the median will be right about in the center. So you can see it. Okay? But notice one thing you cannot see from a box plot. This is important. If the distribution is bimodal, you're not going to see that. And in fact, this could be a bimodal distribution. If things were nice and centered, you would see this. So you can't pick out the number of modes. That's the one place where the box plot falls down. Okay, now, here's the interesting part. Outliers. Okay, so here's the thing about outliers. They are the most screwed up part of statistics. People want to throw them out. You shouldn't do that. Outliers are usually the most interesting portion of the data set, okay? So here's what I want to show you. So notice that we actually have a definition of outlier now. Formally, we have a definition of outlier. It's a data point that's 1.5 fence lengths above the third quartile or 1.5 fence lengths below the first quartile, okay? We were picking them off before using a histogram and saying that they were isolated. But there's a problem with this. Notice that you really can't tell if this is an outlier or this is part of the tail, okay? So there's a little bit of genuine confusion there. So here's the thing. then this is the reason why it's important in finance. It turns out that in financial data, they're very often right skewed. Financial data tends to be very heavily right skewed when you're looking at compensation, when you're looking at human performance. And this is the reason why. It's something called Pareto's principle. So you might not have heard it called Pareto's principle, but a lot of you who have some business experience have heard this saying that 80% of your business comes from 20% of your customers, okay? That's the Pareto principle. It says the majority of the effect comes from the minority of the population. Pareto discovered this. He was an Italian economist in the early part of the 20th century, and he had this like beautiful mind. He just was interested in everything. He was a gardener, and he noticed something one day. He noticed that when he was picking peas, okay, that 80% of his peas, he had this garden, came from 20% of the plants. And he convinced himself it wasn't because he wasn't watering a portion or whatever. They were all kind of uniformly distributed. So he started wondering. He was actually interested in fascism. So at that time, Italy was starting to move toward the fascist regime. He was concerned that a lot of the property was owned by a few percentage of the population. But it turns out that this is kind of a natural consequence. If you look at, for example, people talk about the 5%. How many people have heard of the 5%?
Now the 1%.
It's the what is the 1%?
Pretty much the top majority who owns as equal as the rest of the 90%. Well, 99%.
Yeah, so basically it says that the 1% richest people own 99% of the wealth. And people get really upset about this, but the reality is there was, back in the 1950s, there was a Nobel Prize-winning economist who proved this is a natural consequence of capitalism. Not because it's an evil system where people are mean. This is what happens in capitalism. You get this Pareto principle kicking in. Now you can argue about whether or not it should be that extreme. Should it be 80-20 or 99-1? But you're always going to have this sort of inequality. It's naturally built into capitalism, okay? So this sort of stuff happens naturally, okay? It happens in human performance, okay? So first of all, it happens in compensation. If you look up even the salaries of CEOs, you'll see this sort of really right-skewed distribution. The guys who are head of Google, they make way out here. And the other CEOs, most of them make up here, okay? But you see it in human performance too. Think about where you work. Very often, the majority of work is done by the minority of people. It's certainly true in my field, research. Easily, 80% of the really important results come from 20% of the people. That's definitely true. Let me just show you an example, okay, of what's going on. So this is real data. This is Major League Baseball salaries in 1988 after free agency, okay? Very strongly right-skewed. No doubt about that, unimodal, right? And here's the problem with outliers, okay? So this is what you want to think about. What are we trying to do? We're trying to fit this with a nice curve, right? So we're trying to fit this with a curve that kind of looks like that. It kind of fits this data set nicely, right? So here's the problem. We have to ask ourselves, this isolated value that's occurring way out here, is this an outlier or is this part of the distribution, part of the tail? Probably part of the tail, okay? So we have to kind of think about that. The problem with having really long tails is if you don't have a lot of values, you won't fill out that tail, right? So you can get these sort of gaps.
Isn't that falls under the aspect of it could be three impressions of the range onto that scale itself, but it could be still.
I'm not quite sure what you mean.
But I mean, as it could be that it's so minor that it cannot be plotted. It's not on the plot, but it's there.
We're going to see a case just like that. We're going to see a case just like that in a second. Yeah. So this is one you have to think about. When you see these long tails and you see values that are isolated, you have to think about whether or not it's part of that tail.
It's based on the scale. It's based on the scale of the actual plot itself. It can be up to from the 0, or it can be from the hundreds, or it can be from the thousands.
So hold that thought. So I want to show you something, okay? So here's kind of a data set that maybe is saying what you're talking about.
Well, yes, what I learned is that in 2009. So.
Okay. So here's the thing. Sometimes outliers are part of a tail that's not filled in, but sometimes they can come from a different population. Okay. So sometimes they can represent something from a population, but sometimes they can also represent a trend. Okay. So for example, if you're looking at resistance to a disease, okay, and you find one person that's way outside the others, that person might be a mutant, literally. They might come from a different population, but it also might represent a trend. That's why you don't throw outliers out. This is a classic example. So these are the home runs that were hit back in 1920. What do you notice about this data set when you look at that plot? What's the one thing that really stands out? Yeah, you wouldn't even notice it except for the scale goes way out. So there's one person that's way out here. It's not obvious if it's one, but it is. Who do you think that person was? Do you know? It was Babe Ruth. So we're usually used to thinking about Babe Ruth as being in the later part of the 1920s. But this is when he was coming up. Here's the actual data. If you rank the number of home runs that were hit, notice Babe Ruth had 54. The next person had 19. So he had close to 3 times the number of home runs than anyone else. He had more home runs than any one team put together. So what do we make of Babe Ruth? Was he an alien? Did he come from a different population? No. And he wasn't taking steroids. They didn't exist back then, right? What he was the start of a trend. If you fast forward to 1927, there were a lot of people hitting that many home runs. Hank Greenberg, Lou Gehrig, Jimmy Fox, right? A lot of people are hitting that many. It isn't that unusual. It's incredibly unusual. He was the start of a trend. You wouldn't want to throw him out. He's very interesting. So let me show you something really cool that you might want to think about.
It's based on the skills that the
Not so much. What it's actually based on is kind of like how things are grouped. You're looking at everyone else grouped together, and then a value is kind of far away. So it's more like, and we can actually talk about like what the distance has to be, but that's kind of.
At that point, because we didn't have to keep going and finding every single new event that occurs. But what I'm saying is, it's based on the limitation of your actual scale. It could be up to 600 or 700, 800. I mean, you can make it as it goes, but what I'm saying is, it's based on like the size of the scale.
Not so much, because no matter how you scale it, you'd still see that data point really far away, right? And there are actually ways that you can kind of bring the data in with logarithmic transformations. I'm not going to talk about that. But this guy here is an individual, his name is Nassim Taleb. He wrote a book called The Black Swan. Black swans are very rare, right? And basically he made a small fortune out of looking at outliers. And he wrote this book. And the New York Times said, it's one of the 12 most influential books since World War II. And basically, he made his fortune out of looking at data points that other people threw away. Why? Because he realized they were trends. So things like the housing bubble that burst, there were these sorts of outliers. There were these indicators. But people didn't pay attention. They just said, oh, it's an outlier, and they threw it away, much to their dismay later on. So we don't throw outliers away, okay? Bottom line. Way, but we don't. Let me go back for some reason. There we go. Okay. In other words, if someone wrote down the number wrong, if there's a transcription error, obviously we want to go back and try to figure out what that error was. If we couldn't, and we were obviously convinced, like if you looked at a person that was 400 years old in a data set, you'd say, wow, somebody goofed up. They probably added an extra 0. And you'd either try to find out what the real value was, or you just cancel, right? Nobody's 400 years old. It could be a measurement error. Maybe there's a surge, something happens, you get a really crazy reading, okay? Or again, it's not from the population of interest. If I'm measuring heights of children, and all of a sudden an adult somehow got into the data set, right? I would throw that person out, not because it's an invalid value, but just because they don't belong in the data set that I'm studying, okay? So these are valid reasons. If we can't convince ourselves it's one of these, we have to leave it in. Generally, what we do is we go back and try to figure out why is that data value extreme? What's special about that, okay? Sometimes you can figure it out, sometimes you can't. If you can't, usually we do our analysis with and without the outlier. We want to see how it's going to affect our results, okay? So just to kind of go back to scale, okay? I'm not going to talk about this, but this is something that's useful to know. Very often, and I think this might be what you're talking about, and this is something that I don't like to get into, but I'll just mention this very briefly because you'll see this. Very often you have these really long tails. What people try to do to make the distribution look nicer, to kind of pull in values that are really extreme, is they take the logarithm. of this, okay? So if this is some value x, they'll tend to take the logarithm. And what will happen is when you take the logarithm is it'll make the distribution look a little nicer. It'll kind of pull in the extreme values. I don't like to get into that. The book does talk about it. I'm not going to get into that. And it does change the appearance. It will change the scale. Things that are really far away will get pulled in. It'll look a little nicer. But I think you have to kind of understand what you're really doing to take the log, and I don't want to get into that. That's kind of a whole different topic, right?
I was right.
What's that?
I was right.
It depends. I mean, if you're talking about outliers, when you take the log, it will look less like an outlier. It's possible something that was an outlier, when you take the log, won't look like an outlier.
So it's all based on scale.
In that sense, it is, yeah. But again, you have to be really careful. And just to get rid of an outlier by taking a log is not a good idea. So just to end with, okay, if you look at our F16 data, now we can describe this, right? We say it's unimodal, right skewed, no apparent outlier. Okay. So we're going to come back to talking about the shape and the center on Tuesday. All right. That's pretty much all for today. Do you have any questions? Anything you want to go over? Homework? Anything like that? Everybody good? Okay. Thanks a lot. I will see you later on.
Last class, you mentioned we were going to go over the second part of the assignment.
We're going to do it on Tuesday. Yeah, so I collect the data, and on Tuesday we're going to finish up Active
Okay,
31.
I walked in a little late. I didn't know if I might have missed it.
No,
Okay.
that's okay.
Okay,
That's okay.
cool.
You're all good. Yeah, and I think I posted an announcement too. So on Tuesday we're going to kind of finish up. I want to collect the data.
Okay, and then as far as the homework goes, I feel like it's a little bit different than what we've been learning in class, and I completely missed the meeting up with your student,
Oh yeah, right. Okay. Right.
which was yesterday.
You can hit green, blue, purple.
I'm really not understanding some of it. I've got. I think I'm on question 6 or 7 right now of the 10, and I'm just having a hard time understanding some of the math functions. Like, I don't know. I mean, I'm gonna figure it out tonight. Just
So and always feel.
I'm not getting anything out of it. Is what I mean. I'm just
Okay. Well, so that's that isn't good. So if you want to do that, so there's the email my instructor thing that you can hit. And if you send me that, I can kind of step you through if you're having a problem. And of course, office hours are really good.
Okay.
Coming to office hours, we can kind of talk about it, and
Okay.
we can knock it out really quick.
Do you have office hours today?
I can.
Or it's due tonight is the only issue.
If you feel free, you can ask me now. I mean, I'm free now if you have time.
Yeah.
Okay. Hey, what's up?
Yeah, I'm gonna be quiet for the rest of the semester. I promise you that.
Don't be. No. There's no reason to do that. That's the very last thing I would want. Seriously.
In regards to the homework, as soon as I get my canvas running, I'll go ahead and finish it all.